Hi, my name is Amber, and today myself and my team members Andre, Tim, and Colin will be walking you through our systems engineering team project on exploring lunar lava tubes. Here is a brief outline of the presentation contents before we begin. In the first portion of this presentation, we will be going through the problem definition we developed for this project. So to give everyone a bigger picture of the problem we are addressing throughout this presentation, I want to start by explaining what is currently known about lunar lava tubes and why they are important. Currently, very little is known about lunar lava tubes, as no rover has ever explored the inside of these tubes. All the information we have on lunar lava tubes is from orbiters that have taken pictures of openings called skylights, similar to the one shown on the screen. Lunar lava tubes could potentially allow for long-term human occupation of the moon by shielding astronauts from extreme temperatures and radiation through habitats built around these tubes. For the mission to explore lunar lava tubes with a robotic system, we have identified several stakeholders. The largest of these stakeholders being NASA, as well as other government space agencies that have interest in future moon colonization. Additionally, private space companies could eventually have interest in lunar lava tubes, as well as might provide rockets for launching the cave exploring rover. Furthermore, parts suppliers and contractors will also have stake in this mission. Here are some key objectives we have identified for this mission, which include creating a robotic system that can enter, explore, and map subsurface lunar cavities of an unknown depth and return this information to mission control for evaluation. Displayed now is the CNOPS for this system. The rover would begin by being launched from Earth's surface. Upon reaching the lunar orbit, the landing thrusters would then be ignited. Following a successful landing on the moon, the rover would then charge using solar power. The transport rover would then leave the lander and drive to a lunar lava tube, followed by the transport rover lowering the Cave Explorer rover into the lunar lava tube. The Cave Explorer rover would then explore the tube, while the transport rover continued to transmit data back to NASA. The Cave Explorer would then return to the transport rover and then set off to explore more lunar lava tubes. Top-level requirements we have identified for the rover include the following displayed now on the screen. Some relevant examples we frequently reference when developing our rover include Viper, a rover developed by NASA that will launch in the year 2023 to map distribution of lunar water in the south pole of the moon. Asagumo, a rover being developed by British space company Spacebit, that's current functionality only involves walking 10 meters and taking footage, but eventually will be developed to explore lunar lava tubes. Additionally, we found some of the features used on Martian rovers Curiosity and Perseverance helpful when developing our rover.
Hello, my name is Tim, and I'll be going over part of the decomposition section for this project, specifically the requirements and the morphological matrix. The functional requirements are listed for a rover system, which consists of a larger transportation platform that travels between lava tubes and a smaller cave explorer that maps and obtains data. Essentially, the rover system should be able to enter the lava tubes and collect information such as mineral content, temperature levels, and volumes of water to be sent to mission control. The system should be operable in complete darkness and should be able to charge and collect power from natural resources within the lunar environment. In addition, the system should also be able to traverse the lunar terrain and withstand its environment, which includes microgravity, lunar dust, radiation, and potential meteorite impacts. Shown here are the performance requirements that are important to specify during the mission. A few of the values and ranges that were specified for the system include the max cavity size the system can map, its turn rate, temperature range, data relay speed, top speed, and travel range. Here are the major constraints for a rover system. The entire system should be completely autonomous with manual override in all control areas if needed for emergencies. The system should also limit itself to solar or battery power as radioisotopes become increasingly scarce. There are also limits on propellant types, energy consumption of software processing, budget, and the mission completion date. Here is the morphological matrix for our rover system. The circled options are what we decided to implement into our rover's design. Certain subsystems utilized multiple options in order to optimize and provide a more robust system. A few highlights include the Cave Explorer's use of LiDAR and ground-penetrating radar to map tubes, and his use of alpha particle and neutron spectrometers for analyzing and identifying minerals from a distance. The system will have an aluminum honeycomb structure and will be entirely solar powered. Independent wheel suspension will be used for the transportation platform, while the Cave Explorer will have robotic legs. Wheels will be made of aluminum with cleats and titanium tubing. And lastly, temperature regulation will involve a combination of electric heaters, gold film, and aerogel. Any remaining systems that I haven't mentioned here are all shown on the morphological matrix.
So now that we know the main types of subsystems which are going to be on this mission, let's discuss how they're going to interact with one another. Starting off, we made an n-squared diagram for the 4 main largest subsystems of this mission. This includes the mission control, the lander, the transportation platform, and the cave explorer. They interact with each other mainly as relays. The lander interacts as a communications relay between the rover system and mission control, and the transportation platform and cave explorer work in a symbiotic fashion, which we'll get into later. So the interfaces of the lander are pretty straightforward. The power system sends power and receives power consumption feedback from most of the subsystems, and the navigation computer controls the rover holding bay doors and the rocket thrusters. So the transportation platform also mainly exists as kind of a base of operations for the cave explorer. It provides a way for it to move around, interacting physically with it via holding bay, and provides a method of data relay between the cave explorer and the lander. So the cave explorer has relatively few subsystems, mainly because many of them can be consolidated. The sensor suite sends data inputs to the central computing unit, which then sends control inputs to not only the cave explorer itself, but also the transportation platform. So, moving on from that, how do the requirements flow down? How do we decide these things? Well, we are only considering the rover for this, consisting of the transportation platform and the cave explorer. The subsystems are in 5 main elements, which are the motion, navigation, data transmission, and data collection, power, and lifetime of the system. You'll notice that some of these subsystems are the same between various elements. This isn't an error. For example, the functional requirements for the speed of the transportation platform are going to be very different from the requirements for the speed of the cave explorer. So, let's move on to the trade studies we've conducted, as not all subsystem decisions are very straightforward. So we look to existing examples for inspiration. For example, the communication between the rover and the lander. 6 things were considered: the range, the interference potential between other signals that are already in space, the rate of data transfer, and less important were the directionality of the signal, the reliability of the radio transmitters, since most radio transmitters are pretty reliable systems anyway, and how easy would they be to implement. Would they use a custom communication protocol or not? So this is what we decided on. These are the weightings. There were 5 options considered. Of these 5 options, the UHF custom protocol was the most favorable, given that its data transmission rate was high enough for simultaneous low compression data from all of the sensors, and it had almost the same level of range as VHF, and it even had less potential for interference from outside signals, but slightly more from obstructions. But overall, it had the best performance, so it was chosen.
The second trade study was used to decide which spectrometer system would be best suited for analyzing mineral content in the lunar tubes. 5 different spectrometers were studied, with 10 separately weighted criteria considered. The criteria with the largest weights were selected based on the importance of the mission. These included accuracy, precision, range of materials able to be identified, performance in lunar conditions, and power required for the spectrometers. After all criteria decisions had been filled, the alpha proton X-ray spectrometer was decided to be used as the mineral analyzation spectrometer of choice. Moving on to the concept architecture of this project, a concept design was implemented that is yet to be used in the lunar environment. This design implements a larger transportation platform with a detachable cave explorer used to enter identified lunar lava tubes from both skylight or side entrances. The 2 cylinders on the small arm located in the front of the cave explorer is the neutron spectroscopy system for mineral identification, with a smaller alpha proton X-ray spectrometer to allow for mineral analyzation. The black square at the back is a VHF receiver antenna for receiving direct control inputs from mission control on Earth, and the tall thin one is a 700 MHz UHF transmitter antenna for relaying information back to the lander. The overall length is around 2.5 meters, the chassis length is 2.3 meters, and the solar panel has an area of about 1 square meter, which should be enough to attain power for our needs. The body of the Cave Explorer was designed to be thick to make room for the battery pack, which can easily hold 5 kilowatt hours, allowing us to exceed our range targets. Interesting features in the rover include the spectrometer chosen from our second trade study, the alpha proton X-ray spectrometer, which allows for mineral analyzation with no sample collection required. Panoramic cameras combined with LiDAR will allow for navigation across the lunar surface, mapping surfaces as the rover moves. The transportation platform and Cave Explorer system is also particular to this study, in which the transportation is independent wheel suspension to accommodate for its wider base, and the Cave Explorer has the recognizable legs, another feature that is particular to this project. Requirement verification is also necessary before implementation. This is necessary to confirm that the project will work as expected, especially in lunar conditions. The most basic verification will simply be a visual check and review of drawings, and all code associated with the rover. A physical examination of all attributes, including dimensions of components on both bodies and their associated weights, will then be done. Testing will be completed in similar lunar environments that are expected to be encountered, especially in the extrema of the lunar temperature and radiation ranges. This will include a demonstration of all data collection processes and mapping techniques, and we utilize rugged environments here on Earth to confirm that the rover will be able to handle the lunar landscape. Gathering information about lunar lava tubes is the first step in finding a suitable environment that can be implemented on projects such as NASA's Artemis program. Utilizing systems engineering allows for projects like these to be possible and ultimately feed humanity's exploration techniques as we look to colonize distant environments. Thank you for listening.